You know that fiery spectacle of a spacecraft re-entering Earth's atmosphere? Most of us assume that incredible inferno is all about friction. But that's a mind-bending misconception, a brutal truth that's wildly misunderstood. The real story behind those fireballs is far more astounding, and it's not what you think. It's about kinetic energy conversion, not some simple rubbing against the air. Imagine Orion slamming into our atmosphere at a staggering 25,000 miles per hour. Let that sink in. That's 40 times faster than a passenger jet. This isn't just fast, it's violent. The spacecraft isn't just gently gliding, it's brutally compressing the air in front of it, acting like a giant piston. This violent compression generates immense heat, transforming the very air into a superheated plasma. We're not talking about just hot here. This is a state of matter exceeding 10,000 degrees hotter than the surface of the sun. This plasma state is astonishingly efficient, effectively removing over 99.9% of Orion's kinetic energy before its parachutes even think about deploying, gracefully preventing an uncontrolled impact. And here's another counterintuitive truth that flips everything you thought you knew. It's the blunt shapes of crude capsules that create shockwaves, masterfully pushing this unimaginable heat away from the surface, keeping the interior temperatures perfectly comfortable. Streamlined shapes, surprisingly, would only make re-entry heat far, far worse. This incredible dance of predictable outcomes emerging from seemingly chaotic processes isn't confined to the brutal physics of atmospheric re-entry. Think about a Galton board. You drop approximately 6,000 tiny ball bearings, and each one follows a random walk, a pure 50-50 chance to go left or right at every single peg. Individually, their paths are wildly unpredictable. Yet, collectively, they form a perfectly predictable normal distribution. Why? Because there are vastly, overwhelmingly, more paths that lead to the middle of the board than to the extreme edges, like that one, improbable left-left-left path all the way down. This elegant demonstration of probability wasn't just some curious parlor trick, it was a profound insight for a man named Louis Bachelier. Born in 1870, he looked at financial markets and pioneered mathematical modeling for them, viewing stock prices much like those Galton board balls. Each layer of pegs became a time step, allowing for a wider range of possible prices over time. Bachelier theorized that a stock price's expected future price would follow a normal distribution, centered on its current price, and that this distribution would exquisitely spread out over time. He termed this incredibly powerful concept the radiation of probabilities, and here's the truly mind-blowing connection, the revelation that ties it all together. Bachelier's discovery in 1870 directly mirrored Joseph Fourier's 1822 equation. Fourier's work was a mathematical powerhouse describing heat radiation, the very same phenomenon by which heat disperses from high to low temperature regions. From the terrifying, yet precisely controlled, inferno of Orion shedding its kinetic energy as heat, to the predictable spread of thousands of random ball bearings, to the probabilistic dance of stock prices, the universe reveals its hidden, interconnected patterns. The brutal reality is that fundamental mathematical and physical laws underpin these wildly disparate phenomena, showcasing an astonishing elegance where randomness begets order, and energy, or probability, radiates in astonishingly predictable ways. You've been looking at the universe wrong your entire life. And now, you can't unsee it.